session.
Hi, Priyam. Hi.
Hi. How are you, Chiranjib?
I'm fine. Yeah. How are you?
Yeah, it's a long time.
Yeah. I'll talk to you later after that.
Yeah, sure. So our today's first speaker is Professor Chiranjib Mitra. He has obtained PhD from Tata Institute of Fundamental Research, Mumbai. After that, he moved to Germany as a postdoctoral fellow at Max Planck Institute for the Chemical Physics of Solids and at the Institute of Solid State and Material Science in Dresden. Then he carried out research in magnetic tunnel junction devices. Then he went to University of Cambridge, where he worked at the Device Material Group. He has also worked at the London Center for Nanotechnology, which is affiliated to University College London. And then in 2007, Professor Chiranjib Mitra joined IISER Kolkata as a faculty member. His area of research is diverse, ranging from experimental condensed matter physics to quantum magnetism, strongly correlated electron system, topological insulator. So today he will be talking about entanglement in low dimensional spin system. So
okay. Sorry, the title was slightly changed, but doesn't matter. You can consider entanglement in low dimensional.
It's no problem.
System. Yeah, same
okay,
top.
Yeah.
Thank you. So these will be let me give a brief outline that all the work that will be presented here was done at IISER Kolkata only. One or two measurements were done in Germany at very low temperature. So it will be from these three papers. So let me switch on the, how do I switch on the pointer here? Let's see, pointer options. There's a pointer. Okay, right. So, so the plan of the talk is I will introduce two quantum spin systems and spin qubits, then entanglement in low dimensional spin system, which is spin chains. Then detailed analysis to extract entanglement from the data. So where I talk about magnetic susceptibility as an entanglement witness, and then variation of entanglement with magnetic field, which is quantum phase transition. Quantum information sharing through complementary observables. So that is also something which was novel. And then quantum phase transition and spin systems. Then I will talk about specific heat as an entanglement witness, which we were the first to do all over the world. So then measurement of specific heat close to quantum criticality and quantum discord in Heisenberg spin systems. If I get time, I'll come to discord. Maybe just briefly we will outline that. And quantum discord through susceptibility and heat capacity. Okay, so as we know that things are becoming more challenging with the advent of nanotechnology, things are shrinking, and now we have sort of one of the advantages also is to make things work faster, because if we are making it smaller, then the electron has to travel less distance, so the speed is increasing. But then we are slowly emerging a regime where we are going into nanometer level or sub-nanometer level, where actually quantum physics takes over, and that is advantageous because that will offer the parallelism for computation. So this is, with the advent of technology, this is made possible now. And this is a little old figure, which was basically the Moore's law, Gordon Moore. And he was telling that the electrons per device, or rather the chips per device, per basically say millimeter square or whatever area, will go on increasing with time. And at some point we are reaching the quantum technology regime. So we are well past 2020 now, and we are very much into the quantum technology regime. And the conference also is called Quantum Information and Quantum Technology. So let's see how quantum technology comes into play for information processing. So this, of course, has been introduced. Qubit is just a two-level system, and the advantages we can whereas as opposed to, let me tell a bit of compare a bit of classical as well. That whereas classically you have a bit which is either 0 or 1. Here you can have it in a superposition. The qubit can be in a superposition of alpha 0 plus beta 1, and I'm sure this has been introduced. So any two-level system, it can be classified as a qubit. Okay. So I'll go a bit fast in this section because it's just recap. So some of the qubit candidates, these are some of the qubit candidates. I don't know whether it has been talked about or not, like photon, linear polarization, horizontal and vertical. Prashant, being recorded, na? Hello? Recording has started? Okay, yeah, it's anyway in YouTube, so it will be recorded. Yeah. So then photon polarization, where circular another qubit is circular polarization, where the left and right circularly polarized can be used. Nucleus with the spin of the nucleus, which is either up or down, that can be used. Electron spin also up and down. And why I made it red, because this talk concerns mostly about electron spin. Then any two-level atom, the excited and ground state of a two-level atom can be used. Josephson junction is basically the Cooper pair basically are used as a qubit, and superconducting loop where magnetic flux can also be used as up and down. There are many variety of any other things. Right now I'm working on nitrogen vacancy center, but that is also spin qubit. So yeah, so as you know, like a qubit can be written like that. So it could be a point on anywhere on the block sphere, and a block sphere is represented using density operator formalism in the following way, which is 1/2 identity plus r dot sigma, where this r are basically numbers, which is basically if you use like ri's, or which is 1 to 3, or rx, ry, rz, which are basically just expectation value of this rho times sigma I. Okay, so I haven't written it down explicitly, but that is how it comes out to be. And for a pure state, of course, it will lie on the sphere. And for a maximally mixed state, it will lie at the center of the sphere. Right. Right. Now, in quantum entanglement, basically you have non-classical correlation between two separated parts of a quantum system. Now, by non-classical, I mean it cannot be described by classical physics, and that we will see. We have seen already in the school, but also we'll see here. So a canonical example is the Bell state. So this is one of the canonical examples of the Bell state, is a singlet state. Now, if you have a two-spin system, so as I said, a one-spin system can be expressed as only alpha 0 plus beta 1, where 0, so your 0, have I written somewhere? Yeah, so basically 0 is 1 0 and 1 is 0 1. Get, yeah, so this is 0 is 1 0 and 1 is 0 1. However, when you have a two-spin system or higher dimensional system, you have to write them as tensor product of the two states. So this is the standard basis or computational basis in a two-spin system. The dimensionality will be 4, obviously. So I will show you. I'm sure it has been done also, but I'll show you briefly how it is done. So I can use both the notations. Either 0 is represented as spin up or 1 is represented as spin down. So it is 1 0 and 0 1, and an entangled state can be expressed as this. So this is actually a pure state which is written in the form of an entangled state. When it comes to mixed state, we will see how it is handled. Okay, so it cannot be expressed as a direct product state. So now, so if I have a system like this, A and B are two spin half objects. Imagine like spin up, down, and down up, which is a Bell state. Then the density matrix is written as half of ket and bra of psi. So which is basically this. Okay. And now when we take the reduced density matrix, which also I'm sure was done in the class in one of the tutorials, is that reduced density matrix is basically you trace over one of the parties, like there are two parties A and B, one of the coordinates of one of the parties. And if you trace over B, then you have trace rho A, which is something like this. So it is rho A, this thing can be written as 1001 half. So if you take the one Neumann entropy, it is 1. So for a maximally entangled state, the one Neumann entropy is 1. Okay, for the reduced density matrix. Okay, so now some of the main operations is what are the main operations in a quantum computer? Is that input, which is initialization or this thing, and then manipulation. Actually, so that manipulation often requires in both in Shor's algorithm. If you have studied Shor's algorithm as a part of the school, it is an entangling gate. And then finally a readout, which is a measurement. Okay. So, there is something called a DiVincenzo criteria, or DiVincenzo checklist, which basically says that if you have a, uh, if you want to identify candidates for using in quantum computation, so you must be able to characterize well-defined set of quantum states to be used as qubit. This is basically, yeah. So you need to be able to characterize them, and then prepare suitable states with this set. So basically, this is a initialization bit. Then you carry out quantum evolution, which oftentimes is basically Schrodinger evolution, and that is computation, and then avoid decoherence for long enough to compute, and then read out the results. So these are some of the criteria that has to be met when you design a candidate, select a candidate for using as a quantum computer. Okay, so what are the challenges to make a quantum computer? The challenges is the following: like you need, it's an interdisciplinary system. So basically, you need material synthesis, which is, it could be either inorganic or organic, as the case may be. So for instance, diamond, you need a lot of synthesis. Then experimental technique or instrumentation and integration of that. And of course, the physics, because the physics has to be studied. By that, I mean, like you need to do calculations or simulations or whatever to classify that these are the system which can be used. So for instance, correlations has to be calculated, or various models. So, or, ground states and excitations, these have to be calculated. So the physics is also very important. And then of course, integration of magnetic and optical techniques with nanotechnology. So in all the cases, right now, it is all the quantum computers would use a hybrid system, in the sense, like either you do using microwaves, so basically, or optical, or even using transport or magnetic. So these are the variety of measurement techniques or readout techniques that will be used. So basically, it's also a very challenging task to use all of them in one system. So I'll skip this. Yeah. So now coming back to our system, which is basically we use quantum magnetic systems. What are they? So we use low spin system. The reason why we use low spin systems like spin half or otherwise spin one is that if you have a very large spin system, let's say is equal to 20, then the 2s plus 1, the multiplicity is almost continuous. So we need the system to be as discrete as possible. So now among them, the system have to be low dimensional, because the low dimensional system behave as quantum magnetic system, because higher dimensional like 3D are often can be described classically using Ising models, something like that. So low dimensional systems are necessary as spin chains or spin ladders. Spin chains means basically interaction is only along one chain. So if I have a pencil or a pen, so this is the chain. Of course, it is not that this thick, it is microscopic. And ladders could be like you have two chains and they're connected. So basically, this is all in terms of interaction. And then there are various models, like Ising model is there, which is classical model. Then you have transverse field Ising model. I'll write down in the next few slides. Then Heisenberg model, which is also quantum. Okay. So I have put Heisenberg, I have marked Heisenberg model in red because I'm going to use Heisenberg model for this talk. So when it comes to some system can actually be naturally entangled. Some of the low dimensional spin systems are actually naturally entangled, and entanglement that is present naturally can be actually accessible. Okay, so it can be measured. So this is one thing, and the natural question to ask is that how much entanglement is there in the system? We know that for maximally entangled state, when we quantify in terms of 1 nanometer, it is 1. But many times you may not have a maximally, mostly in nature, you don't have a maximally entangled state. So you have to quantify like how much entanglement is there and how is it distributed in space, and can we use it for anything? So these are some of the things that we need to study. So what happens is, so one of the naturally entangled systems where you have entanglement in nature is the transverse field Ising model. Now in the Ising model, pure Ising model, which is classical, the Hamiltonian is written like that. I do not know if everybody is from physics background, but if you don't, I'm sure you have studied the Pauli spin matrix at least. So basically you have an interaction J, which basically causes two spins at site I and site J. Imagine they are at site 1 and site 2 to interact with each other. They interact with each other because of Coulomb repulsion and Pauli exclusion principle, and that is actually contained in that J. So let me tell you that magnetism as such is a quantum phenomena, but models can be classical because magnetism arises because of Pauli exclusion principle and Coulomb repulsion. So which is so Pauli exclusion principle is inherently quantum mechanical phenomena or nature. So the other thing is the Zeeman term, which is the external magnetic field applied. And in this case, we assume that the external magnetic field applied is also along the Z direction. And we have used sigma Z so that you understand that the two spins can either point up or down only. So these are the only two possible directions that they can point towards. So here this dynamics is non-trivial, which is basically if you write down the Heisenberg equation of motion, which is basically if you calculate the expectation value of any basically the time dependence of the expectation value of anything, you have to commute it with the Hamiltonian, and if it commutes, which means the time dependence, so the non-trivial time dependence is 0. And if it does not commute, which means there is a time dependence in the system. So that is what is a very important thing. Now, what happens in transverse fieldizing model? You apply the external magnetic field, which was here along the z-axis only. Here you apply it along the x-axis. So basically, the spins are along this direction, and the external magnetic field is applied around this direction. So they are perpendicular to each other. And as you know that the Pauli spin matrices do not commute amongst each other. So if you replace the sigma iz by sigma ix, then it is not going to commute, and hence you will have non-trivial quantum dynamics at the lowest temperature. Okay, and in such a scenario, you can also see phenomena like quantum phase tension. We'll talk about later. So our system, so coming back to our experimental work, is that it's copper nitrate. So this is the model of the spin chain. So you have two exchanges here. So let's say this capital J and this small j. Now, let's say, so these two spins are connected by capital J, which is much greater than the small j. And this spin is connected by the small j. You can see here, like these two are, so it's also called exchange coupled pairs. It is a long chain. Of course, you need a many body system. But then what happens is this exchange can be ignored in comparison to this exchange. So this is a very strong exchange. So I'm writing this Hamiltonian as J S1 dot S2 plus capital J S1 dot S2 plus small j S2 dot S3. So this is enough to capture the whole thing. And then there is an external magnetic which is along B along Z direction, and B sum over I SIZ. Okay, this is Pauli spin matrix or the spin operator, which is bar by 2 times Pauli spin matrices. And S1 dot S2 actually are basically, so what is S1? S1 is I S1x plus J S1y plus K S1z. Okay, I don't know if I have written it down. No, I haven't written it down. So that is the idea. And then, so this is also called this diamond spin model or alternating diamond spin model. So basically what you have, these spin, so these two couple strongly with each other, these two couple strongly with each other, these two couple strongly with each other. And there's a very weak coupling here, which can be ignored. Okay. And such a system can form something like this. So this we will return to later. Right. So now if I have, maybe I'll come back to this later. So let me write down the Hamiltonian fully. So the Hamiltonian is J S1 dot S2 plus B. So if I take just two spins, J S1 dot S2 plus B S1Z S2Z. So S1 dot S2, so it's basically h bar by 2. So I'm becoming a particle physicist for the time being. So take h bar equal to 1. So basically it's just 1 by 2. So 1 by 2 times 1 by 2 is 1 by 4. The J is sitting outside. So it's sigma 1x times sigma 2x. So there is no dot here, it's just product, but I have just put the dot here. So because S1 dot S2 gives me sigma 1x, sigma 2x, tensor product plus sigma 1y, sigma 2y, sigma 1z, sigma 2z. And the B is just sigma 1z plus sigma 2z. So basically, if you work this out, now this is a talk. If there was a tutorial, one could actually work this out. if there's a demand, then I can ask one of my students to work this out. So you have this Hamiltonian, which is basically 1. So this part comes out to be 1 minus 1 minus 1, 1, and there are 2 off diagonal terms. So the nature of this Hamiltonian is like X. Okay. So this is a very unusual symmetry which has a lot of relevance in quantum magnetism. So this part contributes to this, and this part contributes to this. So there will be just 2. Sorry, this will be -2. Sorry. So this will be 2 and this is -2. So when I add these two, so it will be j by 4 plus b. This will be j by 4 minus b, and this fellow will be minus j by 4 minus j by 4 and j by 2 j by 2. Now you can see that this Hamiltonian has a block diagonal form, and like this is a square. Okay, I wish I could write here. So this is a square which needs to be diagonalized. This is already in the diagonal because there are no elements here, and this is also in the diagonal with no elements here. So you can straightaway see this is one eigenvalue, which is j by 4 plus b, and this is another eigenvalue, which is j by 4 minus b. Okay, so I have to diagonalize this part, and when I diagonalize this part, okay, so this the eigenvector corresponding to this, since all others are 0, so only this part will contribute. So there will be a 1 here. So one of the eigenvectors is 1 0 0 0, and the eigenvalue is j by 4 plus b, and for this fellow it's j by 4 minus b, and it is 0 0 0 1. So this is down down, this is up up. There are 2 eigenvectors, which is straightforward. When you diagonalize this 2 by 2 matrix, then what you do is you get one of the eigenvectors to be 5 plus, which is 1 by root 2 up down plus down up, and that is 1 by root 2 0 1 1 0, and this has a eigenvalue of j by 4, and this another one is 5 minus, so which is 1 by root 2 up down minus down up, and this is 1 by root 2 0 1 minus 1 0. So these two are the well state, and this is the singlet state. Here the eigenvalue is minus 3j by 4. Now if I put b equal to 0, then what happens? B equal to 0 here, b equal to 0 here. We see that we have a threefold degenerate state with eigenvalue j by 4, and one non-degenerate state with eigenvalue minus 3j by 4. So the thing is, these three belong to the triplet state, and this is the singlet state. So now let me go back. So this is what I was talking about, the singlet state and triplet state. Now triplet state, as you know, has 3 multiplicity, which is minus 1 0 plus 1. Okay, and the singlet state has only one multiplicity 0. Okay, so that is it. So these are the 3 these 3 represent the multiplicities of the triplet state, and this is the singlet state. Okay, so the dimensionality of this matrix is 4, so there will be 4 eigenvectors, 4 eigenvalues, right? So now suppose, okay, now there is a very important point here. So imagine like b equal to 0. So this is j by 4, j by 4, j by 4. Now if j is positive, then what I have is that minus 3j by 4 is the smallest quantity here. Okay, so if j is positive, then minus 3j by 4, and this state is an antiferromagnetic state. Okay, so the ground state here is antiferromagnetic. Okay, and it's a pure state if you are at t equal to 0. So this is the ground state in when j is greater than 0. So in my model, it is antiferromagnetic, so it's a j is greater than 0, and you have a gap, spin gap, or rather energy gap of j between the ground state, singlet state, and the excited state, threefold degenerate triplet state. When you switch on the magnetic field, of course, it's a separate issue, the degeneracy lifts, but this is a threefold degenerate triplet, and there's a non-degenerate singlet. So the spin gap is j here, okay, because minus 3j by 4 and j by 4. So the difference is j. So this is a gap system at the lowest temperature, and if this is the state, then the entanglement is as follows, like rho AB is phi minus, if this is the ground state, and the density matrix is this, and when I take the reduced density matrix, it comes this, and that is maximum missing, which means the state is maximally entangled. So at the lowest temperature, the system is antiferromagnetic, and it is a entangled state, maximally entangled state. Okay. Now, what happens at finite temperature? So let me do the analysis first, then I'll show you the data. 10:30. So I'll go slow, even if I can't cover the whole thing. It is fine. The idea is to understand this. There are these papers which I had mentioned at the beginning, and it's possible to read them and if you want more details. So the density matrix is written by one. So this is a thermal density matrix. The density matrix is written as 1 by Z, phi minus, phi minus. Sorry. So let me tell you how the density matrix is written. Okay. So these are the 4 states. These are the 4 states. 1, 2, 3, and 4. So the density matrix is written as e to the power minus of beta e ket bra ei ei. Okay, e to the power minus beta ei ket bra ei ei. So so this will be ket bra up plus ket bra down plus ket bra phi plus ket bra phi minus, but with suitable eigenvalues going into the weight. Okay, so this is what I have written. So one eigenvalue is so this is e to the power minus 3j by 4. So e to the power minus beta. So minus of minus 3j by 4 is plus 3j by 4 beta. Then phi plus is minus j by 4 beta. This is minus j by 4 minus b beta, and this is up down, and this is minus j by 4 plus b beta. Okay, and the z is trace of rho. This is to normalize the trace. As you know, the property of the trace is that it has to be normalized properly. And these are the states. Okay, eigenstates which are induced. So the density matrix looks like something like this. Again, as I said, it will have the same X form. Okay, X form. So it's also block diagonal, like something like this, and there is one here, because the states in which I am expanding is of that form. Okay, so you can have a look at it, take a screenshot or whatever. There is the most important density matrix that we have to solve. Okay, now what happens at very high temperature? So I have seen what happens at 0 temperature. It has maximally entangled, and so this is the density matrix. This is the other extreme, which is at the highest temperature, and then we'll see what happens at intermediate temperatures. Okay, so at highest temperature, what happens is beta goes to 0. So when beta goes to 0 in this state, when beta goes to 0, you see when beta goes to 0, so this is 1, this is also 1, and these two cancel because 1 minus 1 and 1 minus 1, this is also 1, this is also 1. This is actually 1 plus 1, 2, 1 plus 1, 2 basically. So there is a normalization factor which will take care of that. Okay. So the density, so normalization factor, oh, I'm sorry. There is a mistake here. Okay. So the mistake is there will be a by 2 here, there will be a by 2 here, there will be a by 2 here, there will be a by 2 here. Okay. Otherwise the trace will not be 1. Okay. Right. So I am sorry about that. So where it is 1 plus 1 by 2, so 1. This is also 1 plus 1 by 2, which is 1, and this is 1 by 4. This trace, I mean this the normalization 1 by 4, and this fellow cancels, this fellow cancels. So it reduces to 1 by 4, 1, 1, 1, 1. So this can be written as, see, so this is a trick that we did and we wrote in this paper, Professor Panigay and I. So you can write it as 1, all the components 0, 1, so 1 by 4 of course, 1, this one 1 and all other zeros, this one 1 and all other 0, and this one 1 and all other. Now this is separable. Why? So that's where I'm coming to. So this can be actually written as product of, so sum of product of two density matrix, this belonging to party A, that's Alice, and this belonging to party Bob. So this is a tensor product. So this fellow corresponds to this corresponds to this corresponds to this, and this have a correspondence. So the property is this looks like a density matrix because if I take the trace, the trace is 1. This also looks like a density matrix. This also looks like a density matrix. This also looks like, so all of them look like density matrices. So the form is as follows, that I have some coefficient pi, okay, times rho I A, rho I B, okay, tensor of rho I A, rho I B, and that sums over. So basically, so there is a theorem called the Hahn-Banach separability theorem, which says that rho is separable if it can be expressed as a convex sum of tensor product states of two subsystems, which means I can write it like that. So sum over k pk, rho I k, and rho 1 k, rho 2 k, or rho a k, rho b k. So the thing is, for all what has to be satisfied is sum over k, pk is equal to 1, and all the pk's have to be greater than 0. If you see here, all the pk's are 1 by 4, so which is basically greater than 0. And if you add them, 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, they add up to 1. So this is a convex sum. So which means that at high temperature, the system is not entangled. Okay. So that is the thing. If there is any question, I know it's a new concept, so I can pause and answer this. Are there any questions here? Okay, I'll proceed. So this is called convexity theorem, Hahn-Banach separability theorem. It's a result from functional analysis and in mathematics. So the system is now the thing is, I have this type of term in the Hamiltonian sigma 1 dot sigma 2. So if I take an expectation value of this, so of course sigma 1, which means sigma 1x, sigma 2x, sigma 1y, sigma 2y, and sigma 1z, sigma 2z, and it is basically the expectation value of this individual quantities. Now, if it is separable, then I can write down like this product can be written as can be separated rho 1x, rho 2x, rho 1y, rho 2y. You can, if you want to do it as an exercise, you can just take this density matrix and work it out. Okay, you will see that they are separable. And the thing is, these will go to 0 because the as you know, poly matrices are traceless. Okay, the system is perfectly separable. Now, what happens at intermediate temperature? This is what is the most important aspect, and this is where we I'll have to keep an eye on the watch also. This is what Shomik or Prashant, once 5 minutes are left, please remind me, then I will wind up. Okay, so the thing is, you have the Hamiltonian, and the expectation of the Hamiltonian is called the internal energy. This is a result from thermodynamics, quantum thermodynamics, whatever, quantum statistical mechanics. And the magnetization is defined as m equal to sum. These are spins, remember, sum over I 1 to n and sigma z I. Now, it all depends on how you want to define it. If you want to define it the magnetization per unit site, then you have to divide a 1 by n. Okay, but this is the net magnetization. And again, I have this term in the Hamiltonian, and I take the expectation value of this, which is basically this. And that is, if it's a separable state, it's like this. Now, the thing is, this is where I invoke, okay, you just ignore this. So this is equal to, this is less than or equal to sigma 1 mod, sigma 2 mod. And this is nothing but your triangular inequality or Cauchy-Schwarz inequality. Okay, you all are familiar with Cauchy-Schwarz inequality. This is just the equivalence of Cauchy-Schwarz inequality. And so this fellow is, and as you know, mod of sigma 1 is sigma x, sigma y, sigma z, like mod sigma x square plus sigma y square plus sigma z square. They are all. So if you take that, so that maximum value, remember I had shown the Bloch sphere, the spin can lie on the Bloch sphere. If it lies on the Bloch sphere, then the magnitude is 1. If it does not lie in the Bloch sphere, the magnitude is less than 1. So basically, the maximum value of sigma 1 is 1, maximum value of sigma 2 is also 1, and therefore the product maximum value of the product is 1. So it has to be less than or equal to 1. Okay. Now, if when I write down the Hamiltonian, so the thing is, this is less than or equal to 1, which means this item, like expectation value sigma 1 dot sigma 2 is less than or equal to 1. And what is this? This is the first term of the Hamiltonian. Remember the j times sigma 1 dot sigma 2. So basically, I have written down the Hamiltonian here again, the S1 dot S2. There is a 1 by 4 factor, of course, that will come out, j by 4. So, and then B S1Z. Now, remember that sum over I S1Z expectation value is this magnetization M. So I can replace, when I take the Hamiltonian expectation value, then this will be simply B times M. And so basically, then I take this term on the left side. So basically U minus BM, so U minus BM and divided by NJ. Okay, so I take this J and I divide by N, because if I sum over this, so there is a reason for that, because I want to calculate for one side. This is for one side, but then of course in the Hamiltonian there is N sides. So I divide by N. So this quantity, as I said, this quantity is less than or equal to 1. So therefore your U minus BM by NJ should be less than or equal to 1. But if it violates this inequality, that points toward the fact that this is an entangled state. For an entangled state, it will violate. So this is the criteria that we are using for intermediate thing. This is not my, I didn't give this. I'll tell you who gave this. So this is the paper. So, so basically there are 2-3 papers. So O'Connor and Wooters and Physical Review A63. Now, there is I don't want to get into the details, but there is a measure of entanglement for mixed state called the concurrence. So if you have a density matrix 1, 2, it can be written in the following way. So sigma rho 1 to tilde as, so this can be done only for two parties, bipartite system. So rho 1 to star. So basically it's the conjugate of that. And you multiply by sigma 2 cross sigma 2 here, sigma 2 cross sigma 2. So this is called a spin reverse density matrix. So, so imagine like what is the, so let me just briefly say what is being done. What is the density matrix? If for a pure state, I mean for pure state density matrix, bracket, ket bra, shai. I am operating sigma 2 cross sigma 2 from here. I am operating sigma 2 cross sigma 2 here. Okay. Now both the first sigma 2 will operate on Alice. The second sigma 2 operate on Bob. Same from this side. So both sides I am operating this. That is called a spin reverse density matrix. And then when I calculate the eigenvalue of such a matrix and I rank them, take the root of the eigenvalue and rank them in this form and take the maximum of 0 and this. So this is in the ascending order. Okay. So lambda 1 is greater than lambda 2 is greater than lambda 3 is greater than lambda 4, and I write it that this way. And the maximum of 0 comma this. If this thing is negative, which means it is not entangled. If it is positive, then it is entangled. So the maximum of 0 comma this will give me the value of entanglement. So this was worked out in this paper. Now in a ferromagnet, this is always 0. The entanglement is always 0. And this is again our intuition. And let me give this. So you have this term sigma I dot sigma I.
Can I just stop you and ask a question?
Yes.
Yeah, in the first equation, rho 1, 2, you used sigma 2. Or what about sigma 1? I mean,
oh, no. Sorry. By sigma 2, I mean sigma y.
Okay, sigma y. Okay.
Yeah. So sigma y, so that is again. So normally in quantum computation, we use this. I mean, in physics, we use this nomenclature. Either we use sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z. Okay, sorry about that.
Okay. I understand.
Okay. So now in a ferromagnet, it is 0. So sigma I dot sigma I plus 1. So this is sidewise. Okay. So yeah. So basically, so here sigma 1, sigma 2. So this sigma 1 is basically sigma x I plus sigma, sigma y j plus sigma z k. That I should have taken care of that. So I should have written sigma y. So basically, Connors and Wooters, they use sigma 1, sigma 2. So that's why I use that notation. Sorry.
Yeah, no problem.
So, so this is that. So this is sigma sigma I, which means at site I. So this is basically sigma I vector is means sigma I x plus sigma j plus sigma x plus y plus z, and the product. Now this can be expressed as, so those who are physics students, they will immediately see. So this can be written as sigma I plus at sigma I plus 1 minus plus sigma I minus plus sigma I plus 1 plus. So these are the raising and lowering operators, and they are Hermitian conjugate of each other, as you can see, plus 2 sigma 3. Now 2 sigma 3 is just a number. I will give the number. So if I take the expectation value, so this is like a ferromagnet, right? Up for 2 spins. So if I take the expectation value for them, this will always turn to be 0. Okay. So this is the one which gives me the spin fluctuation. This spin fluctuation is the equivalent of your 0-point oscillation of a harmonic oscillator. So there is no 0-point oscillation here. Okay. For a ferromagnet. So because the order parameter is sigma iz, which is sigma 1z plus sigma 2z, sigma iz commutation with the Hamiltonian is 0. So for an antiferromagnet, so let me tell you, the order parameter is actually not sigma 1z plus sigma 2z, because it will always be 0, because one is up, one is down. So it will always be 0. So what you do, sigma 1z plus minus 1 to the power I times sigma iz. Okay, sigma iz plus I plus 1 or whatever that side is a minus 1 to the power I plus 1. So this is called the staggered magnetization, and for an antiferromagnet, they do not commute with each other, and therefore there is a 0-point oscillation which is equivalent of the entanglement. So for an antiferromagnet, U by Nj is greater than 1, which is an entangled state. So the concurrence, which is this, if you remember, like so u by nj, because I put b equal to 0, external field is 0. So in absence of an external field, so this concurrence formula becomes u by nj minus 1. So whichever is greater. So if it is greater than 1, then it is entangled. It is 0 or less than 1, it is not entangled. That is the entanglement weakness. Okay. So this has already been done. U by nj either is greater than. So for isotropic system, now if you don't apply an external magnetic field, what happens? The system is isotropic in the sense that your I forgot to mention this. So there is a rotational invariance allowed by in the Heisenberg Hamiltonian. So that's the difference between the I should have mentioned that the Ising model and Heisenberg model is that sigma 1 dot sigma 2, which means it is rotationally invariant, means whichever direction you go, it is the same. Okay. So therefore, if the system is isotropic, so sigma 1x, sigma 2, sigma 1x, sigma 2x expectation value, sigma 1y, sigma 2y expectation value. So basically, I can replace all three of them by only one when I'm actually doing my calculation. So, so your this thing, okay. So the expectation value of u is nothing but expectation value S1 dot S2, and for an antiferromagnet can be shown that this is like this, and S1 dot S2 I can actually calculate. I have actually calculated in the paper is basically this, and therefore concurrence comes out to be 0, 1 minus e to the minus beta j. So there is a temperature dependence which is coming into the system, which is the intermediate entanglement. Susceptibility is an entanglement. Now, what is the connection of susceptibility with this? The connection of susceptibility is this. This is the what you call the by fluctuation dissipation theorem, the formula for susceptibility, which can be measured in the lab. Okay, is this G square mu v square n by kBt. Fluctuation dissipation theorem gives me 1 by kBt by 1 by 4 plus S1 dot S2. Now, this is something which is there in the Hamiltonian. You have seen that, and I have calculated this. So this can be easily plugged in, and your concurrence is maximum 0, comma. So because it was half 0, comma u by nj minus 1. So this is half. So it's max 0, 1 minus 6 kBt chi by g square mu square. So I am inverting this, okay, into the system. So this formula was given by Vedral and co-workers in this paper, and I have used this. So basically what happens is, remember that this has to be positive. If this has to be positive, if this has to be positive, then this has to be greater than this. Okay. So I just plot this. So this is that plot. This is a theoretically generated plot. So this is my data. It's, and as I said, the system is antiferromagnetic. So anything less than that, okay, has to be entangled, because this is 1 minus of this, has to be entangled, and anything above is a separable. Okay, so this is what I have shown experimentally. So this is the boundary, theoretically calculated boundary, which says that anything above this is separable, anything below this is entangled. Okay, so this is the entangled region. Okay, so now how did I calculate this? I calculated this using this formula. Okay. So I plug this formula in there, and this is my concurrence, and this and I know, so I have calculated this. This I have calculated. Okay, so this is the theoretical curve. So in this formula, I fitted this green curve, which is the theoretical fit, and this is the experimental value of concurrence or entanglement weakness. It doesn't go up to 1 because it will slowly go and saturate at 0 temperature. It will be nearly 0 temperature, or let's say millikelvin, it will be 1. Okay, so right. So I have I measured only down to 1.8 Kelvin. So this is what you're getting. Okay, so this was done in this paper. Okay, how much time? See. Okay, now there was another paper by Anderson, Bose, and Vedral, and actually we have actually generated this plot, basically replicated this from their graph. So in this curve, there is only temperature dependence. Now we want to have field dependence. How does the field dependence enter? You will see this was done for zero field. Now, if I have field, then you will see. So this is 0 field. When you have field, then you have u minus bm by nj. Okay, so b is there. You cannot ignore this. So what is m? M is sum over I sigma I z. So basically, I have to incorporate that also. So that I incorporated in that, and this is the theoretical plot that I get. So this was the as a function of temperature, and you see it goes like this and comes back, and at say around 5 Kelvin, it becomes 0. Okay. So now if you're J, so let me tell you one thing, that how do I know, how do I model a system or how do I choose a system which will tell me that I can have entanglement till a higher temperature, let's say 20 Kelvin or even 30 Kelvin. So then my J has to be higher. Okay, so J is the one which determines where your entanglement ends as you heat up as a function of temperature, even as a function of field. And if you go like this here as a function of field, then you will see that the entanglement goes down and like that to 0. Okay, so I think there is a better, yeah, this is a better curve. So here you see this is as a function of field. So you can see at very low temperature, it drops very, very sharply here, 0. At the 0 temperature, it will drop very sharply, but as you increase the temperature, slowly there will be a curve like that. Okay, this is the theoretical data. So my data also says something similar. So this is my data. This is the experimental curve of entanglement as a function of temperature and magnetic field. So as a function of magnetic field, it goes down like this. So this is basically capturing something like here. So I am somewhere here, you see, somewhere here in the theoretical curve. I couldn't go down to lower temperature. So if I could go down to lower temperature, then I would get this sharp drop. But you will see in heat capacity, we have gone down to low temperature, there is a sharper drop. So, right. So this is entanglement versus field. Now what is happening? Why is entanglement versus field? As I'm increasing the field, why is entanglement reducing? Okay, that's a natural question to ask. See, temperature I can understand because the correlation are being destroyed by thermal fluctuation. But what about this? So this is as a function of field. So now this is what I would like to explain is that you remember that my eigenstates. So what were the eigenstates? J by 4 plus B, J by 4 minus B. This is J by 4 and this was minus 3J by 4. I should have written it here, but yeah, never mind. So if I increase the field, the eigenvalue goes on increasing like this for this state. Eigenvalue goes on because this is J by 4 minus B, it goes on reducing. And then what happens is at this point, when you have sufficient field, which is basically around 3.5 Tesla, which is a very high field, this crosses over and my ground state, which was an entangled state, which is a singlet state, which was an entangled state, is no longer the ground state. I have a new ground state here, which is the separable state. So my entanglement goes to 0, nearly 0. Okay. At very low temperature, it will drop very sharply, but at higher temperature, it doesn't drop sharply. So I think, yeah, so let me tell what is quantum phase transition. Very, very briefly, because I don't have much time, I will not be able to. How much time do I have, by the way? 10 minutes.
Just 5 to 7 minutes.
5 to 7 minutes, I'll quickly finish. So I'll just explain this very quickly. Is that if you have the Hamiltonian as a parameter, G, then it is H0 plus G, H1, where H0 and H1 commute. Now, if they don't commute, then of course, there will be a level crossing where excited becomes the new ground state, and at G equal to GC, let's say, as a function of this parameter, which is field, then this creates a point of non-relativity of the ground state energy as a function of G. And that is what is the quantum phase transition. So basically, something like this, it crosses over. Okay, so there is a crossover takes place. So the ground state or something like that. This is avoided level crossing, there is a level crossing. So basically, that is what is happening here. You see, this crosses down, and there is a change of the nature. So there is a point of analyticity. There is a change in nature of the ground state, and therefore, so there is a quantum phase transition that is happening. Okay, so let me skip this and quickly go to the heat capacity part. Yeah, heat capacity is an entanglement witness. So what happens here is that in addition to susceptibility, there is another measurement called heat capacity. Now, heat capacity is something that you have studied in terms of liquid heating or ice heating, water heating or ice heating. So the theory is the Hamiltonian is related to the heat capacity as follows. So Cp is 1 by kBT square. This is from the fluctuation dissipation theorem again. H square expectation value minus H expectation value square. So the measure of entanglement is represented by concurrency. The same thing, remember, I had mentioned before, as half max U minus Bm by Nj minus 1. Okay. So if this is positive, then there will be an entanglement. If this is 0 or less than 1, then there will be no entanglement. So entanglement state, in the absence of B equal to 0, it is U by Nj is greater than 1 is the entangled state. And the internal energy is related to the heat capacity by the following formula. Like if I have the heat capacity, if I just do the integration of this curve, as this is T is temperature, then I get the internal energy. So so this is the experimental data, the experimental heat capacity. So basically at very low temperature, okay. Now remember the singlet triplet model. So singlet triplet model. Okay, so at very low temperature system is in the singlet state. Okay, now as you go on increasing the temperature, what happens at certain points, there is excitation from here to there. So the moment it starts, excitation means start absorbing heat, that is heat capacity. Here it does not absorb because there's not enough energy. So it start absorbing heat, therefore the heat capacity increases. And once the system has already got excited, it comes to zero. Now there are two parts of the system, specific heat. One is the spin part, another is the lattice part. So the lattice part was actually, so basically this is the lattice part also. The lattice part was subtracted and therefore we obtained this part. Okay, how did we subtract the lattice part? Well, we did some fitting to the lattice part and subtracted it. So basically, this is the data, which is basically the round circles is the data and the red curve is the fit to the data. Okay, so this was published here, and because here we went down to very low temperature, 0.3 Kelvin, and the measurement was done in Philip Gegenmont's lab at University of Göttingen. So this is the temperature and field dependence. So basically at different fields, so we went up to 7 Tesla, 0 to this thing, and we measured heat capacity up to 7 Tesla as a function of temperature. So this is the curve. Okay, this is the zero field curve. Right. So here also there is a separable region. So this is the heat capacity, and there is a separable region. Remember, I said U minus Pm is greater than 1. So this, so basically this is the entanglement region, and this is the separable region. So this was given theoretically in this paper by Blackwood again. It's a different paper. Okay. So this is I have already mentioned this. So this is the experimental. So let me just say the heat capacity is this. This is the expression for heat capacity, and internal energy is just trace of rho T means the same rho that we have used before times H, which is the Hamiltonian, the expectation value of the Hamiltonian. Okay, so this is U by Nj. Okay, U Nj minus 1. So U by Nj. This is the U by Nj. So it goes like that. Okay, and the concurrence, which is basically half times 0 comma U by Nj minus 1. This is at zero field. Okay, so this goes like that. So remember I said that if I could go to previously I could go to 1.8 Kelvin. Now I have gone to 0.3 Kelvin, and the entanglement is almost equal to 1. Okay, so I've been able to reach a very, very pure state. Okay, so and as I'm heating, okay, so this is 0 T means 0 Tesla, no field here. So it goes down, and at 4 Kelvin, entanglement vanishes. Okay. Let me skip this. Okay. Yeah, this is the internal energy through which so we did this calculation, and the concurrence is like that. So this is the experimental curve, and in between. Right. Now, what about field dependence? So field dependence. So this is the 3D plot of internal energy which we have calculated. Sorry, which we have evaluated. 3D plot. This is the theoretical plot, of course. So this is what is the internal energy, and remember that how the internal energy is connected to concurrence using this formula. Okay, but here this will be U minus Bm when the field is there. Okay, so I evaluated U. So this is the heat capacity curves at various temperatures. These are the experimental data at various magnetic field, and how did we calculate the internal energy? By integrating this Cp T times Tt. Okay, so and we use this formula and calculated so this is entanglement witness at various magnetic field as a function of temperature. So at 7 Tesla, you see there is absolutely no entanglement even at the 0 temperature. So therefore, you remember this curve, right? So there is a problem like so if I go as a function of field at very low temperature, it drops very sharp, but at higher temperature, it drops slowly. So this is heat capacity as a function of field. So basically, yeah. So as I go as a function of field, this is the quantum phase transition of 3.5 Tesla. It almost goes to 0. Remember, this is the magnetic heat capacity. Okay, there is no lattice part here. So it goes up, comes down, again goes up, comes down. But that is natural because after that it is no, there is no entanglement at all. So basically, if I plot the so this is the experimental curve and the theoretical curve. So this is where the quantum phase transition this happens, and this is the entanglement across QPT. As I said, like 0.8 Kelvin, 0.3 Kelvin data was not that good, so therefore 0.5 also 0.8 was good. So you see, this red curve is the theory, and these are the experimental curve with the error bar, and there's a sharp drop in entanglement across the quantum phase times. Okay, great. I think Priyam, I will not go into the quantum discord because it will take a long time. So I can do one thing. I can show that there through quantum discord also. We have showed. I mean, this is basically correlation and quantum discord. Through quantum discord also we calculated as a function of temperature. Okay. So, but I don't want to get into that because it will take another 15 minutes to do. So before I end the talk, I just want to say that, yeah, there was a paper which appeared in Nature Physics, which has cited, you can see 1, 2, 3, 4, 5 of our paper, which is really good. And Nature Physics asked me to write a article based on that, which is long distance entanglement. Basically, the same in the Heisenberg Hamiltonian using the same picture that I have shown in this thing. So what happens is there are a lot of dimers. They can be weakly coupled, and then it can give long distance. I have only considered nearest neighbor coupling, but it can actually generate long distance entanglement doing this. Okay. Right. I think, yeah. So to summarize, the antiferromagnetic ground state is entangled. Magnetic circuitry can be used as entanglement witness. Using quantum mechanical uncertainty, this part I did not talk about. So specific heat measurements at low temperature explicitly captures quantum phase transition. And we are the first person to use specific heat as an entanglement witness experimentally. We didn't talk about quantum discord. So these are the people who are involved in the papers that we have presented, and they're my former students, and Philip Gegenberg was a collaborator. Thank you. Yeah.
Okay. Thank you, Professor Mitra, for enlightening us about the entanglement in quantum spin system as well as the corresponding quantum phase transition. So is there any question from the participants?
Can I ask a question?
Yeah, please.
Yes. Thank you for your talk. What about the level of noise present in spin qubit systems? Because noise should introduce additional error, and how it is managed.
So here I have given the error bars. So the point is, let me tell you, this is not a noise. Noise will be a factor when you're measuring single spins. This is an ensemble measurement. You understand the difference between ensemble measurement and single spin measurement, right? So you are measuring 10 to the 23 spins here. So noise will not be that important. And this for susceptibility, I had used QIQT. So the level of noise that is there is 10 to the power minus 8 EMU, and I am measuring 10 to the power minus 3 EMU. So electromagnetic unit. So it's much less. So in this particular thing, it will not matter because it was a macroscopic measurement. I should have emphasized that there is a macroscopic quantum entanglement criteria, same for specificity. So noise will not be that major a criteria here because it's an ensemble measurement. If you go to single space level, which of course we are doing right now, then it will be a criteria.
Thank you. Last quick question. Can we see the impact of weak or strong entanglement on realization of quantum algorithms.
Can you speak a little louder once again?
Yes, yes. Can we see the impact of weak or strong entanglement on realization of quantum algorithm?
Quantum algorithm.
Yes, because you were talking about the entanglement. So if entanglement is weak or strong, so what will be the impact on
I
quantum
can
algorithm?
definitely answer that question, though this is not my domain. But see, when you do a computation, what you do basically is there's a very good paper by Bennett and DiVincenzo. It's a Nature paper where actually what is computation? So in quantum mechanics. So basically we have the state and you allow the states to evolve. Now what is the so basically let's say you have the Heisenberg Hamiltonian and how so basically you allow it to evolve using a unitary rotation or unitary evolution. What is the unitary evolution? U is equal to power minus of I capital H by H bar times T. So you switch on the interaction for whatever time. Now, if there is, let's say, Heisenberg Hamiltonian, so how do you have strong entanglement, weak entanglement? So strong entanglement happens at low temperature. As I said, like lowest temperature. So the entanglement is, let's say you are here, okay, and supposing you are here. So when you are doing some algorithm which is like computation, then obviously you will have more errors coming up here. You have like entanglement which is maximum at this temperature. Can you see the screen? So I think the let's see. If you are not in presentation mode, can you actually let me go back to presentation mode. Can I actually use the pointer?
No, I can see the cursor, so it's okay.
So if you're somewhere here, so obviously your full interaction will be there. So your computation will be faster and more effective. If you are somewhere here, obviously, as you are talking about noise, so there will be errors, more errors that will propagate into your algorithm. Okay. So into your computation. So obviously you want to have the strongest interaction. You want to have the most strongest entire state. So that is the thing. That's all.
Okay, thank you.
Okay. So as we are running out of time, we'll keep the for later. You can always catch up Professor Mitra later on.
Yeah, the papers. So basically, if I just do one thing, like you can take a screenshot of these three papers. Okay, so you can just take a screenshot of these three papers and read them later. Okay.
Yeah.
Right.
So let us thank Professor Mitra for an interesting topics. Okay.
Thank you. Okay.
Yeah. So now ARC postdoctoral fellowship and an ARC future fellowship